Hello everyone, today we're going to talk about the principle of inclusion exclusion, which is a form of strategic overcounting to help solve a problem in a simpler method. Alright, let's start with our first example. If there are 20 people in my school's chess club, 25 people are in my school's art club, and 11 people are in both clubs, how many people are in the chess club or the art club? Alright, so one way to go about this would be using a Venn diagram, but I'm going to show you a simpler method. So normally what we could do is we could just add the number of people in this chess club, which is 20, plus the number of people in the art club, which is 25. However, if we just do this, we're going to count the people that are in both clubs one extra time. So to get rid of this, we can just subtract 11 people that are in both clubs, leaving us with 34. And it's just that simple. That was a simple example of the principle of inclusion exclusion. Now let's try a harder example. My state uses a sequence of 3 letters followed by a sequence of 3 numbers as a standard license plate pattern. For example, GMQ829. Then each three-letter 3-digit arrangement is equally likely. Find the probability that a license plate will contain at least one palindrome, a 3-letter arrangement or a 3-digit arrangement that reads the same left to right as it does right to left. So in this situation, we have 2 cases. The first case is in which the letters are in palindromical format, and the second case is in which the numbers are in a palindromical format. So what we can start by doing is counting how many ways are there for the letters to be in a palindrome sequence. In this case, we have 26 choices for the first letter times 26 choices for the second letter, and then the third letter has to be the same thing as the first letter, making that constant. And then along with this, we have the numbers which you have to account for, which is just 10 to the power of 3. So this, we'll count this again later. And now this is for the first case. And now for the second case, in which the numbers are in a palindrome format. For this case, what we'll do is we'll check 10 choices for the first number times another 10 choices for the second number, and then the third number has to be the same thing as the first, so I don't need to count that again. Now similarly, we have to count for the letters, which is 26 times 26 times 26, which is just 26 cubed. So now what we have to do is, if we just add these up, we will be overcounting the cases in which we have both the numbers and the letters being in a palindrome format. So what we have to do now is we have to subtract off the cases in which there is a palindrome for both, which is in the case where we have 10 times 10 for the numbers, 10 squared, times 26 times 26 for the letters, 26 squared. And our answer should just be the first one plus the second one minus the third one, meaning that our numerator, since we're asked the probability, is 26 squared times 10 cubed plus 26 cubed times 10 squared minus 26 squared times 10 squared, divided by our total, which is just 26 cubed times 10 cubed. So what we can do is we can take out 10 squared times 26 squared. We can take that out common, leaving us with 10 plus 26 minus 1 over 10 times 26, which is just 260, which simplifies to 35 over 260, which is just 7 over 52. And that's it.